What's up? Here we are at the end of chapter 6, so it's time for a review. Let's get started. Number 1 is going to come out of section 6.1. So if you need any additional examples, check out that section. The probability distribution for a random variable x, the number of medical tests performed on a randomly selected outpatient at a certain hospital, is given here. And so we can see that we have either 0 number of tests, that's a 33% chance, 1 number of tests, that's a 20% chance, 2 tests, that's 18%, and so on. So we need to describe the probability that x is less than or equal to 3 in words. So what that means is the probability that 3 or fewer medical tests are performed. That's what that is asking us, and we're going to find out the value. The probability that x is less than or equal to 3. So less than or equal to 3 would be those 4, so 3, 2, 1, or 0 medical tests. All I need to do is add up those 3 probabilities, and that'll give me the answer, which is 0.85. The next question here says, what is the express the event performing at least 2 tests in terms of x. So that would be x is greater than or equal to 2. And then I'm going to find the probability of that. Again, I just need to look at greater than or equal to 2, and that would be 0.18 plus 0.14 plus 0.12 plus 0.03, and that is 0.47. And there's number 1. Number 2. The mean height of players in the National Basketball Association is about 79 inches, and the standard deviation is 3.5 inches. Assume the distribution of heights is approximately normal. Let h be the height of a randomly selected NBA player. We need to find and interpret the probability that the height, h, is greater than 74. Because I was told that the distribution is approximately normal, I can draw myself a bell curve. The mean of this bell curve is 79. The standard deviation is 3.5. It's asking me to find the probability that the height is greater than 74. 74 is probably going to be around here, and I'm going greater than 74. So that is all of this. Before I even plug this into the calculator, I should be able to recognize that this is going to be greater than 50%. The probability that h is greater than 74, I'm going to go to my calculator under normal CDF. That's under second vars. It's going to ask for the lower boundary, that is 74. The upper boundary is infinity. Guys, make sure you're using the scientific E, not the alpha E. The mean of this distribution is 79. The standard deviation is 3.5. I plug all of this into my calculator. So I go over here, and I'm going to go to second vars, normal CDF. My lower boundary, again, was 74. My upper boundary was infinity. Again, the scientific E is second and the comma. It's little like this. 99. The mean of this distribution was 79, and the standard deviation was 3.5. Plug all that in, and there's my answer. 0.9234. 0.9234. We do get the fun of interpreting this. This means that the probability that a randomly selected NBA player is taller than 74 inches is 0.9234. So there's a pretty good chance that we're going to randomly select an NBA player that is taller than 74 inches. Number 3. Number 3, we have we have Spencer. Let's see, there we go. Spencer is running the balloon darts game at the school fair. He has blown up hundreds of balloons with notes about prize tickets inside them. 12% of the notes say you win 5 tickets. 20% of the notes say you win 3 tickets. And the rest say, sorry, try again. After each play, he replaces the pop balloon with another one bearing the same note. Let T equal the number of tickets won by a randomly selected player of this game. Now, this one asks us to actually give the probability distribution for T. That means we have to come up with a chart ourselves. It's not too bad. So we're going to have the number of tickets, and then we're going to have the probability of winning that number of tickets. So the first part of this tells us that you win 5 tickets has a probability of 12%, or 0.12. The next part tells us you win 3 tickets has a probability of 20%, and the rest say, sorry, try again, therefore you're winning no tickets on that one. So in order to find this missing probability, I just need to take 1 and subtract 0.2 and subtract 0.12. That's going to give me the leftover probability, which is 0.68, and that goes right there. So there's our probability distribution for this situation. Now I need to find the mean and the standard deviation of this distribution. In order to do this, guys, we're going to use our calculator. We're going to plug in these values of number of tickets into L1, and we're going to plug the probabilities into L2. All right, so let's go and do that. Alrighty, so I'm going to go to Stat, Edit, and into L1. Let me clear my list here. I'm going to clear that list as well. And into L1, I'm going to put in 5, 3, and 0. And into L2, I'm going to put the probabilities associated with those, 0.12, 0.2, and 0.68. Once my probabilities are in here, I'm going to go to Stat, Calc. Now this is only one variable, so I am going to go to one variable. However, the frequency for each variable is different, so I need to make sure an L2 is there. If you don't already have an L2 there, you're going to want to go to second and the number 2. You hit calculate, and here we are. Now, the mean of T, this is part B, find and interpret the mean of T. It doesn't say mean of T in my calculator, but X bar is the mean. So my mean here is 1.2. Standard deviation, which is actually found in part C of this question, is 1.833. Okay, so let's write those down. We have here that the mean of T equals 1.2. Again, that was listed as X bar in my calculator. And down here, the standard deviation of T, that was 1.833. Now we do get to interpret. So if we play many games, we will win 1.2 tickets on average. And the typical variance is 1.833 tickets. So we should not be surprised, guys, if we play this game and we never win any tickets. That should not be surprising to us. We should also not be surprised if we happen to win 3 tickets. Now, if we win 5 tickets, we might be a little surprised. That was number 3. Let's look at number 4. The total sales on a randomly selected day at Joy's Toy Shop can be represented by the continuous random variable S, which has a normal distribution with a mean of 3,600 and a standard deviation of 500. We need to find and interpret the probability that S is greater than 4,000. So we have a normal distribution, we have a mean of 3,600, and we have a standard deviation of 500. And we're looking for what is the probability that the total sales is greater than 4,000. So here's 4,000. We're going greater than that. To find this probability that S is greater than 4,000, we're going to use normal CDF. Normal CDF, the lower boundary is 4,000. The upper boundary is infinity. The mean of this distribution is 3,600. The standard deviation is 500. I'm going to plug this into my calculator. Second vars, normal CDF, the lower boundary 4,000, the upper boundary infinity, the mean 3,600, standard deviation 500, and my answer is 0.2119. Okay. 0.2119. We get to interpret it. The probability that the total sales on a randomly selected day is more than $4,000 is 0.2119. And that is number 4. All right, now all of those questions, number 1, 2, 3, and 4, all came out of section 6.1 from this chapter. So if you need any extra help on any of those, I would look over 6.1. All right, let's continue. Number 5. The manager of a children's puppet theater has determined that the number of adult tickets he sells for a Saturday afternoon show is a random variable with the mean of 28.3 tickets and a standard deviation of 5.3. Now that was for the adult tickets. The mean and number of children's tickets that he sells is 42.5 with a standard deviation of 8.1. So this first question here, part A, is about the adult tickets. The adult tickets sell for $10 each. We're going to let A equal the money he collects from adult tickets on a random Saturday. What is the mean and the standard deviation of A? All right, so we have the original distribution, and it had a mean of 28.3 tickets. It had a standard deviation of 5.3 tickets. Okay, now our transformation here, A equals 10 times that original distribution. All right, so for the mean, if I multiply by 10, that will affect the mean. So the mean of the adult distribution is going to be 10 times the mean of that original distribution. The standard deviation, when I multiply a distribution by 10, the standard deviation does get multiplied. So I'm going to take the standard deviation of that original distribution and multiply by 10. So here's where I'm going to do my calculations. 10 times 28.3. and 10 times 5.3. So now I'm going to have my new mean and my new standard deviation. The new mean of the distribution of A, which is the money he collects, is $283. The standard deviation of that is $53. This is the new mean and the new standard deviation after I multiply each of those ticket sales by 10. All right, now we're going to talk about for the children. The original value for the children, the original mean was 42.5, and the original standard deviation was 8.1. Now it says here that the children's tickets are $6 each. And C is the money he collects for children's tickets. So C equals 6 times the children's distribution. Now I am just using Y for the children because I did use X up here for the adults. So I'm just going to use Y just because I want to make sure we don't get confused. All right, so the mean for the children's distribution is 6 times the mean for the original children's ticket sales. Again, 6 times the original is going to convert the mean by 6. Standard deviation is also going to be converted by 6. So 6 times the standard deviation of the original. I'm going to do my calculations. So I do 6 times 42.5 and 6 times 8.1. My new distribution, the mean for the children's dollar amount that he collects is $255 with a standard deviation of 48.6. So now I know not only how many tickets he sells, but I also know how much money he makes, which is probably what he really cares about. All right, guys, if you want some more information about this, you can look under section 6.2 in this chapter. Number 6. Let's look at number 6. The random variable W is normally distributed with a mean of 46 and a standard deviation of 23. The random variable Z is defined by Z equals 11 minus 8W. What is the mean and the standard deviation of Z? So again, we have an original distribution, and this original distribution has a mean of 46 and a standard deviation of 23. We need to make a transformation of Z equals 11 minus 8W. So that means for the mean of Z, now the mean is affected by multiplication, division, addition, and subtraction. So the mean, I just have to plug in the original mean of W, which is 46. So that calculation is simply 11 minus 8 times 46. And when I plug that into my calculator, the new mean of Z equals negative 357. It's totally fine to have a negative mean. That's not a big deal. You cannot have a negative standard deviation, however, but your mean can be negative. Now, the standard deviation of Z is going to equal, now, if I do addition or subtraction, which is what's happening right here, that does not affect the standard deviation. So all I have to do for the standard deviation is do 8 times the original standard deviation of W. So I just have to take 8 and multiply by 23, and my new standard deviation is 184. So again, I'm just going to write a little note here that addition and subtraction does not affect standard deviation. So So that is why you do not see that 11 minus on that standard deviation row. Again, if you want more information on this or you want to review your notes for this, this is under 6.2 as well. All right, number 7. Number 7 is a doozy because number 7 is multiple steps that you have to do in order to get the answer. So we're going to go through each and every one of those steps. Mr. Watkins and Mr. Wessling bowl every Tuesday night. Over the past few years, Mr. Watkins' scores have been approximately normally distributed with a mean of 212 and a standard deviation of 31. During the same period, Mr. Wessling's scores have also been approximately normally distributed with a mean of 230 and a standard deviation of 40. Assuming their scores are independent, what is the probability that Mr. Watkins scores higher than Mr. Wessling on a randomly selected Tuesday night? All right, guys, so the first thing is I want to just kind of write down what I've been told and then kind of what the question is. So I've got Mr. Watkins and Mr. Wessling. I'm going to call Mr. Watkins a K because there's the K in his name, and I'm going to call Mr. Wessling a T. All right, so that's how I'm going to distinguish between their two distributions. All right, so let me make that T orange. Okay, so the mean for Mr. Watkins is a 212, and the standard deviation for Mr. Watkins is a 31. The mean for Mr. Wessling is 230, and the standard deviation for Mr. Wessling is 40. The question that has been presented to us is to find the probability that Mr. Watkins scores higher than Mr. Wessling. That's what we're having to do here. Now, when we combine two different distributions, we don't really look at like how they are one's greater than the other. So what I need to do here is I need to subtract this T from both sides. And now I have the probability that K minus T distribution, this is a single distribution here, is greater than 0. Okay, so whenever I subtract that T, it is going to give me a 0 on the other side. Okay, so K minus T is the new combined distribution. Okay, so that's going to be our new combined distribution. So that means that I need to find the mean of the combined distribution for K minus T. And I need to find the standard deviation of the combined distribution of K minus T. And so, to do that, I'm going to take the mean for Mr. Watkins and subtract the mean for Mr. Wessling. And that is just taking 212 and subtracting 230. That is negative 18. Now what that means is that on average, Mr. Wessling is going to score 18 more points than Mr. Watkins. That's on any average Tuesday night. Okay, that's why it's negative, and that's okay that it's negative. It just means that the second number was bigger than the first. Now for the standard deviation, I do combine them just like I always combine standard deviations. I'm going to take the standard deviation and square it. And then I'm going to add the next standard deviation squared. And then I combine them together and take the square root. So we have the square root of 31 squared plus 40 squared. And when I plug that in our calculator, we get 50.6. So now I have a brand new distribution. This brand new distribution is approximately normal because both of the original distributions were normal. And this is the K minus T distribution. This is the combined distribution of K minus T. The mean of K minus T is negative 18. The standard deviation of K minus T is 50.6. So as you can see here, on any given Tuesday night, it could be that Mr. Wessling beats Mr. Watkins. That's not completely out of the picture, all right, because we have a mean of -18 with a standard deviation of 50. So that's definitely something that could happen. Now, the probability that K minus T is greater than 0. So I'm going to go to 0 on my distribution, which would be over here. And I want the probability that I am greater than that in this distribution. That is anywhere in this spot is when Mr. Wessling is going to win. Okay. 0 is when they tie. 0 is when K equals T, just so you know. All right, so all I have to do, normal CDF, excuse me, the lower boundary here is 0. The upper boundary is infinity. The mean of this distribution is -18, and the standard deviation is 50.6. This is going to be the probability that Mr. Watkins scores higher than Mr. Wessling. All of these on this side of this distribution is when Mr. Watkins is scoring higher than Mr. Wessling. The probability is 0.361. So see, it's not completely out of the norm for this to happen. This happens 36% of the time. Now, I am going to tell you guys to put a big giant star next to this one because there is one extremely similar to this on your test tomorrow. Alrighty, let's look at number 8. Ms. Lakey likes to drink coffee in the morning. Yes, she does. She prefers to drink it with cream and sugar. The distribution of calories for coffee, cream, and sugar are all approximately normal. The mean and standard deviation for each distribution is shown in the table below. The calories of the items are assumed to be independent. So we have coffee, cream, and sugar. So it says here that the random variable T is the total calories for Ms. Lakey's morning coffee, which includes 1 serving of coffee. So I'm going to have 1 serving of coffee, 2 servings of cream, and 3 servings of sugar. Find the mean and the standard deviation of the total distribution. So what we're going to do first is we're going to transform these by the number of servings that I like to use each morning in my coffee. So the first thing we're going to do is for this coffee. Now, I only use 1 serving of coffee, which is what all of these numbers are. These are all for 1 serving. So I don't have to change the mean for the coffee, all right? Let's see, for coffee, let's go ahead and use an F, and we'll use C for cream, and we'll use S for sugar. So the mean for the total number of servings that I'm going to use just for the coffee is still 5, and the standard deviation is still 2. I don't have to do anything with those because I only use 1 serving of the coffee. Now for the cream, I'm going to use 2 servings. So I need to multiply each of these by 2. So that means the mean for the cream is going to be 220 calories, and the standard deviation for the cream is going to be 18. For the sugar, I'm going to use 3 servings. Multiplication does affect the mean and the standard deviation, so I'm going to multiply both of those by 3. The mean for the sugar is going to be 255. The standard deviation for the sugar is going to be 45. Now I just need to combine them all together. So the mean for the total cup of coffee, I'm going to take the mean for the coffee itself plus the mean for the 2 servings of cream and the mean for the 3 servings of sugar. I'm going to add those up. So I've got 5 calories from coffee, 220 calories from cream, and 255 calories from sugar. That gives me a total of 480 calories on average in my cup of coffee. Now I need to put all of the standard deviations together. So I'm going to have the standard deviation of the 1 serving of coffee squared, plus the standard deviation for the 2 servings of cream squared, plus the standard deviation for the 3 servings of sugar squared. I'll combine those all by adding them up, and then I'll take their square root. So I have the big giant square root of 2 squared plus 18 squared plus 45 squared. And when you get that answer, you should get 48.5 calories. So you should not be surprised, or I should not be surprised, I guess, if my coffee has 500 calories in it. I should not be surprised if it has 450 calories in it, but I should be surprised if it only has 400 calories in it, or if it has 550 calories or more. That's number 8. Again, there is one very similar to this one on your test tomorrow. Please be prepared for that. All right. All of number 5, 6, 7, and 8 come from chapter 6.2. So if you need more information on any of those, check that section out. Alrighty, let's look at number 9. We are now moving into the part of the review that is over 6.3, which is our most recent section. All right, so this should be very familiar. A manufacturer produces a large number of toasters. From past experience, the manufacturer knows that approximately 2% are defective. In a quality control procedure, we randomly select 20 toasters for testing. Determine if this distribution is binomial or geometric. Well, first of all, we want to double check, does it satisfy the binary success and failure? So it's kind of weird here, but success, or what we're counting basically, is whether or not they're defective. So that would be success is defective, failure is not defective. We do have independent toasters. Each toaster is going to be independent of every other toaster that we look at. And then here's the game changer. Is it N for number of trials is fixed, or is it T for the trials until success? It tells us here that we have selected 20 toasters. So we have N, we have a number of trials, and those are predetermined of 20. Our success probability, well, it tells us that 2% are defective, so our success probability is fixed, and that is 0.02. That's our success probability. Looks like, guys, this is binomial. This is binomial. The determining factor was right here, whether or not we had a set number of trials or whether or not we had trials until success. The parameters for a binomial distribution are N and P. Okay, so N, that's our number of trials. P, our probability of success. You have N and P for your parameters for a binomial distribution. All right, let's look at the next part. We need to find the mean and the standard deviation of this distribution and interpret those. The mean of a binomial distribution is I need to take N and multiply by P. N is 20, P is 0.02, and when I multiply those together, I get 0.4. What that means is if we select many sets of 20 toasters, about 0.4 will be defective on average. So obviously, guys, you can't select one set of 20 and have 0.4 of a toaster be defective. Excuse me. So obviously what this means is if I take many sets of 20, maybe sometimes none of them will be defective, but sometimes one of them will be defective. So usually it's going to be around one or none-ish. The standard deviation for a binomial situation. Standard deviation is n times p times 1 minus p. That equals the square root of 20 times probability of success times probability of failure. So 1 minus 0.02 is 0.98. And when I do this, I get 0.626. That means the typical variance is 0.626 defective toasters. So again, if I get one that's defective, I should not be shocked out of 20. If I get 0 that are defective, I should not be shocked out of 20. But if I get 2 or more that are defective, I'm probably going to be surprised. Last question here says, what is the probability that exactly one of the toasters is defective? This is the probability that x equals 1. One success or one defective toaster. Now, the formula on the formula chart says n choose x, p to the x power, 1 minus p to the n minus x. So if you want to do this that way, then you would do 20, choose 1, because we have 20 trials, we're choosing 1 defective. Probability of success or defection is 0.02 to the 1, because I only have 1 success or 1 defective. Then I would have 0.98, that's the probability of failure, that's 1 minus p. And I would have 19 of those that are successful that are not that are not defective. So I can do it that way, okay? Or you are more than welcome to use the binomial PDF command in your calculator. That is under second VARS, binomial PDF. For most of you, that's going to be option A. It's going to ask you, what is your number of trials? That's 20. It's going to ask you for P, the probability of success. That's 0.02. And it's going to ask you for your X value. That's how many successes or how many defective toasters are there. Either way, guys, whichever way you do this, you're going to get the same answer, okay? And that answer is going to be 0.2725. Alrighty. If you want more information on how to do that one, check out 6.3. We actually did a few different ones of these on our 6.3 workout. We actually did 2 of those that were very similar to that, so check those out. All right, let's look at the last problem. Determine whether each variable below is binomial, geometric, or neither. Draw a card from a standard deck of 52 playing cards, observe the card, and return the card to the deck. That's important. And shuffle. Count the number of times you draw a card in this manner until you observe a jack. Looks like we have a clear success and failure. Success is I have a jack. Failure is not a jack. We do have independent draws. What I draw does not hinge upon what I have already drawn because I am returning the card to the deck. So just because I have already gotten a certain number or a jack or not doesn't change whether or not I'm going to get another jack. Now, do we have N or do we have T? What I'm asking here is, do we have a set number of trials, or am I doing trials until success? I am doing trials until success. So I do not have a set number of trials. I have trials until a jack. Once I get a jack, I'm done. Now, is my success probability the same? Is it fixed? The success probability is fixed because, again, I am returning the card to the deck every time. There are 4 jacks in a deck of cards out of 52 cards, so my success probability of getting a jack is 4 out of 52. This is geometric. This is a geometric distribution. Our next problem, Joey buys a lottery ticket every week. X is the number of times in a year that he wins a prize. All right, do we have success and failure? Success is he wins. Failure is that he does not win. Each week the lottery is independent of any other weeks, so we have independent plays. Now, do we have N or T? Is there a set number of trials? Well, it says in a year, every week. So we have a number of trials that equals 52, because there's 52 weeks in a year. And then our success probability. The success probability, what is the probability of winning the lottery? Well, I'll tell you, it is very big, and it's not worth playing the lottery. But I will also tell you, it depends on the number of people that play. The success probability changes each week. So this is neither. This is not binomial or geometric because it fails the success probability. Part C. Suppose that one of every 100 people in a large community is infected with HIV. You want to identify an HIV positive person to include in a study of an experimental new drug. How many individuals would you expect to have to interview in order to find the first person who is HIV positive? All right, we do have a clear success and failure. Success is HIV, failure is non-HIV. I know that sounds really strange, but that's what was given to us. Each person is independent. We have independent people. N or T, which one do we have? Do we have a set number of people we're going to test, or are we going to do trials until success? It says here, how many individuals would you expect to have to interview in order to find the first person who is HIV positive? We're going to do trials until first HIV case. Once I get that first HIV case, I'm done. I've got my person, and I'm going to include them in my experimental trial. Our success probability. It tells us here that 1 out of every 100 people is infected. So my success probability would be 1 out of 100. It looks like we have ourselves another geometric distribution. For our final one, you are on Interstate 635 in Dallas, counting the occupants in every 5th car that you pass. Let Z equal the number of cars you pass that has more than 2 occupants. You continue until you have counted 20 cars' occupants. We have success and failure. Success is more than 2 occupants. Failure is not more than 2 occupants. Okay. We do have independent cars. All right, do we have a set number of trials or trials until success? It tells us we're going to do this 20 times, so it looks like we have a number of trials of N equals 20. Now, what about our success probability? What is the probability that I drive past a car and they have more than 2 occupants? It is unknown. Therefore, fail. This is neither. It was kind of looking binomial, but it failed. All right, you guys. Excuse me, I'm so tired. I need to go take a nap. You guys have a fantastic time reviewing, and I will see you on your test. Good luck. You're going to do great. Bye.